questions for the discussion at the end. So let me introduce the next speaker, Dr. Ricardez-Sandoval. He is currently a professor at the Department of Chemical Engineering at the University of Waterloo, so he's coming all the way from Canada, where he currently holds a Canada Research Chair professorship in multi-scale modeling and process systems engineering. So Louis has multiple publications, more than 190, and actually has some already some nice awards in his resume: the NSERC Discovery Accelerator Supplement and the Ontario Early Research Award. And I'm looking forward to your talk.
Thank you, Maria. Okay, so good afternoon, everyone. First of all, I would like to thank Shi and again Rafik for organizing this workshop that is really interesting to catch up, of course, with good friends and new friends that we make every time that we meet. So thank you very much for the invitation. I really appreciate it. So what I would like to do today is that I would like to show you some work that we've been developing for quite a few years now. I don't recall actually the year when we started doing this. I think it was back in maybe 2018, 2019. And basically right now, this particular framework that we developed is getting mature. We're getting some interesting results. So basically I want to show you, most of my talk will be focused more on the applications, because that's what I want to see. What I'm interested to see, for example, is some of the people in the audience, for example, is interested in exploring these applications with this method. That is what basically motivates most of my discussion, rather than discussing the specific internal, 90-degree details of the methodology that have been already posted in a GitHub in my group. But anyways, let me get started. Alright, so this is just a brief outline of my talk. So first of all, I will give an introduction. Then I will basically introduce the basic framework. Nowadays, again, we have evolved. This is something that is called the Discrete-Steepest descent algorithm, the D-SDA. And again, nowadays we have different versions of this D-SDA. And again, I would like to focus more on the application so that you can see the kind of features, characteristics that this particular method can handle, and again the type of results that we get, and finally some final remarks, and then also show you where we're considering, or we have already considered the application of this method for some new applications. Okay, so ordered discrete structures. So most of us, again, we have dealt with discrete decisions, right? Like whether should we, for example, consider something or not in a particular process. I'm talking more about chemical engineering. So basically, when we have something that is an ordered discrete decision, and for those of you who are chemical engineering, the classical example, of course, is a distillation column, where basically we have the feed and we have a number of stages, and maybe the question here is, okay, where should I, for example, introduce the feed location, right? Where should I basically locate the feed that will enter in this distillation column? So that by itself, it's a discrete decision. Of course, these are trays, these are physical trays, that basically is just a number, an integer decision again. And if we want to solve this problem in, let's say, the standard, the conventional way, most of what we will do, for example, is that we will consider each one of these variables and represent the number of stages. So I will represent each one of these variables as either a Boolean or at least a binary variable. So in this case, for example, typically Booleans are represented as binaries. So for example, here I will represent, for example, Y3 as a single binary variable that will basically determine if the feed stream will enter in, for example, tray number 3, yes or no. That's the type of decision that we make. And of course, if I have n stages, that will basically force me to develop n basically Boolean decisions for this particular problem. This particular problem, again, is an ordered discrete decision, because as you can see here, there is an order, right? So I have n stages, and one of the stages is one after the other. So again, there is a sequence. There is not going to be, for example, a distillation column that will have a hole in the middle. and for that reason, again, we call it, again, 8 ordered discrete decisions. So if I want to represent this in a mathematical form, so well, we have here the form that basically, again, yi belongs to OD set and is an ordered set. And then, of course, we have the assignment constraint that basically exactly one yi are true, which again represents the Boolean decisions. Again, this is just basically saying that the ordered discrete variables are a combination of integer variables plus these external variables. Now, in chemical engineering, we have different applications, right? What I showed you is just one of them. But for example, something else that is an ordered discrete decision involves, for example, this problem, which again I will show you later the results. So basically, we have a reactor superstructure. I want to determine, for example, how many reactors I need, and if I need, for example, to consider recycle in one of these reactors, so that I can, for example, achieve a certain product purity. So again, this is a problem that again we can formulate with these Boolean variables, and again that is where these binary decisions will come into play. Obviously, the problem grows because if you have a lot of binary decisions, then of course the problem becomes a bit more difficult to solve. So we also, we can also have this problem, for example, in a stage-wide heat exchanger network, and obviously, of course, in an optimal design of a catalytic distillation column. All right. Also, these problems appear in scheduling, and this is one of the applications that we recently found or were exploring, actually, nowadays. And basically, we're observing, and again, we're getting some interesting results. So in this case, for example, for batch processes, right, if the batching, for example, happens in this unit J and I have a task, if these tasks, for example, have a certain processing time, right, then, and again, since this task is going to be continuously be done on that unit J, then of course I can consider that, or we can reformulate this as an ordered discrete type of decision. And of course, in this case, for example, I can determine the processing time for each one of these tasks that will be assigned to this unit J. So again, in this case, for example, again, the ordered discrete variables, if, for example, I am assuming, if I am taking into account the dynamics of each one of these batches, for example, if I'm looking at the evolution of the batch, and if I, for example, I want to control the temperature in, let's say, a reactor, then of course I will have to consider transient operation. And for that reason, of course, I will have a nonlinear problem. And at the end of the day, combined with my Boolean variables, it will return a mixed-integer nonlinear optimization problem. Alright, so the question is, okay, so what can we do with existing MINLP algorithms? Well, the first thing that we can say is that yes, for some of these problems we can solve ordered discrete decisions. However, the current solvers, for example, they often fail to efficiently explore the search region for this particular application, for ordered discrete variables. They rely on the continuous relaxation of these ordered discrete structures. For example, they cannot optimize purely discrete variables. For example, the number of stages in RAFRAG, which is again something that we use quite often in Aspen Plug to again model rigorously distillation columns. Or, for example, sometimes we might face also convergence issues, right? That basically we fail to identify solutions, feasible solutions, even when we provide a very solid, a very good initial, very well-educated initial guess, right? So again, that is where this MINLP, if we want to use the conventional MINLP algorithm, this is where, again, these methods, we might have a hard time finding solutions. So what we are proposing here basically is an alternative, is a framework, is some sort of like a methodology, right? That basically we want to develop an efficient and a practical MINLP solutions, an alternative to the existing solvers that circumvent the current limitations in those problems. In particular, what we want to use is that we want to exploit this idea of that the problem itself has ordered discrete decisions. So in that case, we're going to borrow concepts and tools for discrete complex analysis, and that's called D-SDA. This is again an optimization framework that has been out there for quite a while and has been used widely for multiple integer programming applications. And in our group, in collaborations with other groups, in particular in the US and in Latin America, we are developing these DCA methods for MINLP, again, mostly driven by the chemical engineering applications. All right, so let me just delve a bit into the math, into the methodology. So as I mentioned earlier, right, we are going to have a group of ordered Boolean variables, and the key idea in this particular method is that I'm going to reformulate all these ordered Boolean variables with something that we are going to call external variables. And these external variables are going to be defined as integer variables in the problem. So now, instead of having a bunch here of, for example, Boolean variables, and for example, each one of these will have a 0, 0, 0, 0, and maybe only one of them will have a value of 1, which basically will tell me, for example, in the case of the distillation column, what is the feed stream. I'm going to represent all this set of binary variables with a single external integer decision variable. Alright? So that is the key idea in this problem. So again, we're going to basically group all these ordered Boolean variables, alright, with a single integer variable that we're going to call E. Alright? The feasible region, if I go back, this is by the way the formal optimization problem, right? Defined as a function of these external variables. And again, the feasible region, in this case S, basically is defined by non-linear constraints. That's another feature in the problem. Alright, so let me try to motivate you or motivate discrete complex analysis. It's just an illustrative example. Again, I'm not aiming to give you a whole theory on this. Imagine that we have this problem. That is a very simple toy example. This toy example again has basically the only decision variable is this variable E, right? That is bounded between this number and again is an integer value. Alright? So if you were to use the traditional solvers, semi-MLP solvers, right, we are going to relax, or typically the solvers will relax this integer decision, right, and will make it real. And as you will see, for example, we will have multiple local solutions that, of course, do not belong to the real set of solutions. Alright? Therefore, again, global optimality, of course, is not guaranteed. In our case, what we're going to do, and that is the key idea of discrete complex analysis, is that we are going to strictly consider these points, right, as basically discrete points. And what I'm going to do in some sense is that we're going to be this kind of region, right, which again by itself will have some convex properties, and that's hence the name, right? And the idea here, the basic idea, is that we are going to start exploring the neighbors around, for example, a trial point, something that we call a trial point. And we're going to do this exploration of each one of these neighbors, and depending on whether we see an improvement in the objective function, of course, provided that we satisfy constraints, then we're going to basically start moving from one trial point to another up until we don't see further improvement in the objective function. So that is the basic, simple idea. Of course, there is a lot of math, there is a lot of theoretical development that, again, we have worked in that way and that has been published. But basically, that is the key idea. So again, we are going to treat this as convex, right? As a convex problem. Therefore, we can guarantee local optimality if, again, we can reformulate this problem as a discrete convex analysis. And don't forget that the key idea here, and I want to make it that clear, is that it needs to belong to an ordered discrete set of values. All right? The problem itself, they must have this property. All right. So let me again explain with this simple example how does it work. So basically imagine, for example, that this E1 and this E2 are two external variables that I have been again, that represents E1 and E2, for example, represents combinations of Boolean variables in my original problem. So I'm going to choose a combination, which is this one here. And when I fix these values, right, when I fix those external variables, then the remaining variables, which in some sense are easier to solve, basically could be a mix of binary, integer, or maybe just continuous variables, then I'm going to solve for the remaining variables. The expectation is that that problem that I'm going to solve when I fix these two variables is going to be a problem that, again, in principle is easier to solve. Still, it's going to be an optimization problem, and then of course I'm going to get the solution. And then what I'm going to do is that I'm going to basically do an exploration around the neighbors that surround this point. As you can imagine, and again, that is still something that we're investigating, we can have different type of neighbors. For example, neighbors that I will only explore the very, very corners, the cardinality points, for example, in this case, for example, these ones, and I'm going to neglect explorations on these other points. This is what we call an N2 neighborhood. the size is 2n, so basically this 2n represents the number of trials that we have to do in order to decide how to move in this particular region, basically where to go from this trial point to another. If we want to do an infinite neighborhood, which basically means I'm going to explore every single neighbor that I can come up with around this point. Again, in this case, for example, if we have just a 2 dimensions, we're going to have something like this. So each one of these points represents, again, a potential neighbor. And don't forget that each red dot that you see here represents still an optimization problem. All right? Could be NLP, could be an LP, or could be, again, a full MINLP if we also consider integer decisions in each one of these guys. All right, so I want to make it clear. For that reason, the set, well, if we are doing this what we call the infinite neighborhood, and as you can imagine, for example, this is one of the original limitations that we have in our approach, is that if we want to basically guarantee convexity, guarantee that we were exploring the full neighborhood, then of course this methodology could be very, very intensive. Basically, the size goes 3 to the n, where of course n represents the number of ordered discrete variables. So, in very simple brief terms, what we are doing is that I have a master problem, which basically the master problem solves for the external variables, right? E1 and E2, right? Of course, subject to that domain, only to the external variables, which is again, if you're familiar with this is some sort of more related to some more similar to Bender's decomposition. And then, of course, I fix these variables, which, for example, in Bender's are called complicated variables. And then the remaining subproblems, once I fix these, once again, could be an MINLP or an NLP. I solve this, and then, of course, I'm going to get values for the objective function. And those values represent, again, characteristics or properties that I'm going to assign to each one of these points. So, again, that is the basic idea. Nowadays, we have developed multiple versions of this particular problem. So, what I'm going to show you here is, again, I would say one of the most recent versions of it, basically just doing one-step jumps. We are going to use Bender cuts or a version of those Bender cuts so that I can basically move a bit faster in my search. Still using the very basic idea, the essence, which has discrete convex analysis. So the idea here is that, of course, in step 1, I'm going to decide if this function evaluated in this neighborhood, again, of external variables, is a minimum over the neighborhood. And if it's not, of course, if we're initializing the method, then I'm going to start basically doing my trials, right? I'm going to basically start exploring a neighborhood. This point, again, represents a solution of an optimization problem. And now that I have this point, I'm going to start designing, or I'm going to start adding cuts, all right? Cuts to my solution. And again, I'm going to basically have some sort of like a database of previous cuts that I have done in previous iterations. And every time I am adding a new cut. Nowadays, we have something that is called the multiple Bender decomposition, where we can actually add multiple cuts at the same time. In this case, I'm just showing basically let's say, one of the original versions of this. Once I add that cut, then I solve basically my master problem. When I solve my master problem, When I solve my master problem, that, as you can see here, is going to allow me to jump from this point up until this new point here. Alright? And basically, this new point will represent, again, in principle, an improvement. It's kind of improving my objective function if I want to minimize. But now, what I need to do again is solve the corresponding subproblem here and in some of the neighborhoods around. Right? That's what I would call E2. Of course, if I observe a significant improvement, or if I don't see any improvement in my objective function, then I will stop. Otherwise, I will continue. So in this case, basically, I have to go back and continue, and that is the way that the method works. And again, this is just a very simple representation of how, in very simple terms, in a graphical format, how the method works. In this case, for example, again, I just want to make it clear, it's just a single cut. Nowadays, we can add multiple cuts as we are performing the search. Something else that is really important to mention about this method is that we need to start from a feasible point, right? We have to start from a feasible point. If we don't have a feasible point, we have also developed methods nowadays using these codes that will allow me to search or to find an initial guess that is feasible, and then from that initial guess I start basically my search. Okay, so now let me jump into the application. This was the very first application that we have for the D-SDA. This is again a very simple problem in some sense, that basically I want to determine the optimal position of the recycled streams and the optimal number of reactors such that I can achieve a certain product quality. Alright? So if I were to formally solve this problem, I'm going to use Boolean variables, which again are binary variables, combinations of binary variables between the recycled stream. The reactors, in this case, I just want to minimize total capacity subject to again meeting my product quality constraint. A very simple reaction. Again, the objective here is not make it complicated, instead make a simple problem that will have the key ingredients that will allow me to demonstrate some of the issues. So again, this is just a very basic formulation. This was done many years ago. But basically, again, we reformulate all these possible combinations of my Boolean variables, of my original Boolean variables, with these external variables. And each one of these external variables, integer decisions, will represent combinations between different reactors. Whether, for example, I should include or not a reactor. For example, as you can see in this case, I have a bypass for this, which basically means I don't consider any reactors. And of course, in this case, I am considering a recycled stream. Oh. All right. So again, this was an original result. We started from a point that again was feasible, and basically it was moving neighbor by neighbor, trial point by trial point. The blue circles here represent the feasible region for this problem, and this was the optimal solution. And as you can see, the method moved relatively fast. In 3.3 seconds, we were able to reach to our optimal solution. We tested this with DICOP, and DICOP took at least double the time of our method. And as you can see, again, DICOP was basically using a different strategy to basically arrive to the optimal solution. Okay, let me move to the next application. This one is again motivated by using a more complex problem. In this case, a catalytic distillation column, of course, which is a classical example of process intensification. Typically, for example, the reactive zone in these problems is fixed. Basically, we say, okay, we're going to have like a reactive zone and then a physical separation zone. However, of course, there is no guarantee that this will give us the optimal design. So in this case, basically what we are trying to do is that we're trying to find the optimal location of each one of these stages, the reactive stages, combined of course with the optimal location of the physical separation stages. In the same way, we want to find the optimal location of the ethanol and butenes. In this case, we were producing ETBE, and again, this was the reactive zone. So in this case, we solved the problem under two types of models. In this case, we connected this with Aspen. So we have an Aspen plus Ragfrak model, which is an equilibrium model. We solve this problem in GAMS. And on instance 2, we basically solve a more formal problem using a rate-based solution. So we took all this information from Aspen, but the model itself was implemented on GAMS. And in this case, again, it was a rigorous model considering basically all the hydrodynamics, the thermodynamic properties, and so on. We basically took those and we implemented everything on GAMS. So these are the three types of examples, or these are the three types of solutions that we get. First of all, this is the initial design that was reported for this problem. Of course, it was all this steady state, by the way. We are not considering any dynamics. Again, in this case, as you can see, the three catalytic stages are together. Then, when we use our approach for an equilibrium-based optimal design, as you can see now, the stages, the reactive stages, are separated as far as from each other as possible. And then when we take into account race-based optimal design, we observe that again the design was a bit different, right? A larger column, so that we can accommodate more physical conditions. Basically, with D-SDA, it took us 540 seconds to solve, and DICOP actually failed to find a solution. Moreover, well, again, when we took this solution, the rate-based optimal solution, and now we basically use these designs, we obtain infeasible designs. What does that mean? That of course, if you already know that you have a rate-based model and that's the way that you should model your system, you might want to use that one as well, although of course it's more complicated, orders of magnitude more complicated. Something that is really important is that the MINLP solvers available in GAMS couldn't find the optimal solution that we found with the D-SDA. They were able to find solutions, but they were not as good as the one that we found by the D-SDA. Alright, so then we took that particular problem and we took it to the next level, and then we said, and again for those of you who knows me, I do a lot of work in optimal process integration, so we say, okay, we want now to take into account dynamics, right? We want to take into account transient decisions. So in this case, we have a model, right, that considers again the fixed rate location as design variables. Where should we basically go back and do the recycle, the number of catalytic stages, and moreover, we wanted to consider the optimal dynamic operation, which basically means we wanted to look at different, already? 3 minutes? Okay, so I have to go fast. Okay, so basically I have to take into account the optimal transitions that happens, because in this case I have a multi-product, multi-grade catalytic distillation column. So again, we have dynamic transitions, a steady state, so we have to solve a simultaneous design and control problem. So we have an objective function. We have an objective function. In this particular case, we use our version of the equilibrium model that we established on GAMS, and I will show you the why in a moment. This is the methodology, which again is just a version of the original D-SDA. I'm not going to go into the details because Marianne is asking me to rush, which is fine. This is the reason why, I don't know if you guys can see it, this model basically to find the optimal design and control for this multi-grade catalytic column, it took us 111 hours to find that solution. So again, it was a very, very challenging problem that again we obtained some infeasible solutions. This is just to show you that basically the dynamic transitions we have to use again scheduled PID controller, because using a single controller didn't work, and again that is not breaking news obviously. But again, this is just showing that the dynamic transitions are smooth and we were able to accomplish all the grades that we wanted to get. Alright, this is another recent application. So in this case, we wanted to do scheduling and dynamic optimization making basically exploit the fact that we can represent this problem as an ordered discrete decision. So in this case, for example, of course, if I have a task here and I have some dynamics, for example, some reactor, if I fix that time a priori, then maybe I might be losing the economics, I might not be able to reach my target, or if I put a very, very long time, basically I might be wasting time that I can be using for other operations. So in this case, again, we use our approach, we use the D-SDA, we were able to represent it again as a discrete-steepest descent algorithm. We basically took some problems for the literature. In this case, for example, we consider the two types of reactors, the small and the large. Each one of those reactors have a different number of hours. We discretized the hours, by the way. So again, these were external variables defined a priori in the problem. So, and the open loop actions basically were the killing and killing duties of each one of these reactors. So those were the transient decisions. So basically what we found is that the DICOP, the monolithic original problem, we couldn't find an optimal solution. With the traditional D-SDA, the original one, we find the solution, the optimal solution, that took us 25,000 seconds. However, with these revised strategies that we're proposing, we were able to find the same solution in very, very short periods of time. So again, this is just part of the solution that basically proves that we are basically meeting exactly the product quality that we needed in the time that was allotted to us. Okay, so this is just a list of the publications that we have published for this particular method. Again, it has evolved over the years. As I mentioned, this is not I would say that it's not like a two-man show. This is basically, when I say two-man, it's my PhD student, David Lignan. So, first of all, I would like to again mention that this is a joint collaboration between the University of Waterloo, Purdue University, Carnegie Mellon, and Universidad de Los Andes in Colombia. So we have different versions of this method now available on my GitHub, my GitLab section. So again, this is free software, so you guys can go and download it. If you're interested, again, we were able to solve this I'm going to skip this for the moment, but basically the idea is that we can connect this with Aspen Plus. We have done it, and it's working. All right? So with this, I would like to acknowledge again all the people who have contributed to this project. More important, I would like to acknowledge my research group, because of course, without them, who we are. All right? Thank you very much for your time, and sorry, Marianne, if it took more than expected. Thank you for your time.